Welcome to the space where we tackle the universe's biggest questions, not just with complex math, but with clear thought. Imagine trying to catch a beam of light. It sounds like a philosophical puzzle, right? But for the great thinkers who wrestled with the nature of reality, it was the genesis of a fundamental truth. We all feel the relentless march of time, that steady, unbroken rhythm we live by. But what happens to that rhythm when you push against the ultimate cosmic speed limit, the speed of light? This isn't just a thought experiment from a dusty textbook. It's a reality baked into the fabric of space-time itself. If you could accelerate, what would you observe? Would distances shrink? Would mass swell? And most intriguing of all, would your watch slow down or stop completely? If exploring the deep mechanics of the cosmos at this pace resonates with you, hitting that subtle like and subscribe helps us keep these cosmic conversations going. Settle in. Let's find out what happens to time when you get closer to the impossible. What happens to time when you push against the impossible speed limit of the universe? Tonight, we dive into the answer, starting with the singular law that forces time to bend. We are focusing on the nature of time itself, not the hours on your clock, but the rhythm of the universe. Time feels constant, an unwavering beat, yet it is intimately tied to one single, massive number, the speed of light. Think about that faint glow from a distant star reaching your eye. That light is moving at a velocity of nearly 300,000 kilometers per second. To put that speed into perspective, light could circle the Earth 7.5 times in just 1 second. It's a velocity so extreme it seems to exist outside the scale of our normal lives. But here is the most crucial fact about this speed. It is absolute. It is the cosmic speed limit, and nothing with mass can ever truly reach it. For decades, scientists imagined a simple physical rule. If you move toward a light beam, you should see it moving past you slower. If you moved at half the speed of light, you should see the light move at only half its regular speed. This seems like common sense. But in the late 18th century and early 20th century, physics proved this intuition completely wrong. Light always moves at the exact same speed, regardless of how fast you, the observer, are moving toward it or away from it. This rule, this unshakable constancy, is the foundation of special relativity, and it has profound consequences. If light's speed is a fixed constant, and it is then something else must change to accommodate our motion, that something else is the very fabric of space-time. To grasp why time must bend, let's use a classic thought experiment often called the light clock. Imagine you are in a high-speed train, moving silently and smoothly across a vast, flat landscape. Inside the train, you have a specialized clock. This clock does not use gears or springs. It uses light. A small flash of light shoots from the floor, bounces off a mirror on the ceiling, and returns to the floor. The time it takes for this light to complete the round trip defines one tick of your clock. To you, sitting inside the train, the path of the light is perfectly straight, up and down. Now, consider a different observer, someone standing on the ground outside the train, watching you pass. For this outside observer, the moment the light leaves the floor, the train is moving forward. By the time the light reaches the mirror has moved. By the time the light returns to the floor has moved further still. To the outside observer, the light did not travel in a straight, vertical line. It traveled a diagonal path up, over, and down, making the total distance the light traveled much longer. Remember the one unbreakable rule: light must travel at the same speed for both you and the outside observer. If the light has to travel a longer distance, the diagonal path, but is moving at the same speed, it must take more time. This is not an illusion. It is a physical necessity. For the fundamental law of the universe that light's speed is constant to remain true, the outside observer must see the train's clock ticking slower than their own. This phenomenon is called time dilation, or the stretching of time due to motion. The faster you move through space, the slower you move through time. It is the universe's way of ensuring that every observer, everywhere, measures the speed of light to be exactly 299,792,458 meters per second. This is not merely theoretical math cooked up by Albert Einstein. It's an everyday reality we have to account for. The most common example is the Global Positioning System, or GPS. The GPS satellites orbit the Earth at a speed of approximately 14,000 kilometers per hour. Because of this high velocity, the clocks on the satellites tick slightly slower than the clocks on Earth due to the time dilation we just discussed. But motion is not the only thing that affects time. Gravity also plays a role. The GPS satellites are also further away from Earth's center, where gravity is slightly weaker. According to Einstein's general relativity, the weaker the gravity, the faster time flows. The engineers who built the GPS system must account for both effects: velocity, time runs slower, time dilation, and gravity, time runs faster, gravitational dilation. The combined effect is significant. If these tiny differences, amounting to only 38 microseconds per day, that is, 38 millionths of a second, were not constantly corrected, your GPS device would be useless. The navigation errors would accumulate quickly, and within a single day, your reported position would be off by several kilometers. Time dilation is therefore a practical, measurable, and essential part of modern technology. Time is not a steady, universal rhythm. It is flexible, adjusting its pace depending on where you are and how you are moving in the gravitational landscape of the cosmos. Now, let's return to the ultimate question posed by our title. What happens when you reach the speed of light? If moving faster slows time down, then what happens at the cosmic speed limit itself? While we, as objects with mass, can never truly reach that speed, we can ask what the physical reality is for a particle of light, a photon. For the photon, which is moving at the maximum possible velocity, a curious thing happens. From the outside observer's perspective, our perspective, the photon's journey can take billions of years. A light beam leaving a galaxy 100 million light years away will take 100 million years to reach our telescopes. But what about the photon itself? According to the equations of special relativity, if an object could reach the speed of light, its mass would become infinite, and the passage of time for it would cease entirely. For the photon, which naturally moves at this speed, the entire universe undergoes extreme contraction. Imagine that photon leaving its star and heading toward your eye. From the photon's perspective, the distance between the star and your eye contracts to zero. The vastness of space between the star and your retina disappears completely. Therefore, for the photon, its entire cosmic journey, crossing billions of miles and millions of years, is instantaneous. It is born and absorbed in the same moment. It experiences no duration, no in-between. It simply exists outside of time's flow. This is the stillness we speak of. At the speed of light, time does not slow down, it halts. The photon is the ultimate time traveler, experiencing the beginning and the end of its journey as one single, unified event. This is not a poetic idea. It is a direct consequence of light's constant speed and the geometry of our universe. This stillness within the photon gives us a profound way to look at the night sky. When we talk about cosmic distances, we don't use miles or kilometers, we use light years. A light year is not a unit of time, it is a measure of distance, how far a beam of light travels in one Earth year. That distance is immense, nearly 9,500 billion kilometers. If we look at a star that is 10 light years away, the light we are seeing tonight has been traveling for 10 years. We are not seeing the star as it is now, but as it was 10 years ago. The further we look, the deeper into the past we see. When you glimpse the Andromeda galaxy, the light hitting your eye left that galaxy 2.5 million years ago. That is longer than our own species, Homo sapiens, has existed. Your act of stargazing is literally an act of time travel. Every sparkle is an echo. Every shimmering point of light is a memory. This is the cosmic paradox. Light, which is inherently timeless from its own perspective, is the mechanism that allows us to witness the deep history of the universe from our perspective. We have established that time is flexible and defined by light in the vastness of space. But what about the time inside of you? The human body, too, is built around rhythm, cycles, and clocks. Inside every organism, from simple bacteria to complex human beings, there are sophisticated internal timers known as biological rhythms. These rhythms control virtually every bodily function. When you get hungry, when your muscles are strongest, when your liver filters toxins, and when you feel sleepy, these processes do not happen randomly. They are meticulously timed. At the most fundamental level, your cells count time. They divide, repair DNA, and renew according to strict schedules. Deep within your cellular machinery are specific genes, often called clock genes, that switch on and off in cycles measured in hours. These cycles ensure that your internal chemistry is perfectly optimized for the demands of the day and the restoration of the night. Your heart, for instance, ticks like a fluid metronome, beating approximately 60 to 100 times per minute when you are at rest. This heartbeat changes in response to your emotions and activities, but the underlying cycle is constant and critical for your life. Even your breath follows a rhythm, a gentle cycle of in and out that calms and coordinates your entire nervous system. Your body is a synchronized orchestra of dozens of internal clocks. So, how do all these separate biological clocks stay in perfect coordination? How does the liver know when the stomach needs to be ready? And how does the brain know when the muscles should rest? The answer lies with a tiny but incredibly powerful structure in your brain, known as the suprachiasmatic nucleus, or the SCN. The SCN acts as your body's master clock. It is the central timekeeper that coordinates all the other smaller, peripheral clocks in your organs and tissues. Crucially, the SCN's rhythm is primarily set by one thing: light. When light hits your eyes, specialized receptors distinct from the rods and cones that help you see send signals directly to the SCN. This is the mechanism that synchronizes your internal time with the external world's time. When the sun rises and the light intensity increases, the SCN signals your body to increase alertness and raise your core temperature. When the sun sets and light fades, the SCN initiates a cascade of changes, notably the release of the hormone melatonin, which signals your body to cool down and prepare for sleep. This approximately 24-hour cycle is your circadian rhythm, a dance between the light of the cosmos and the biology of your cells. This rhythm is millions of years old, an inherited mechanism that ensures your survival by keeping you in sync with the Earth's rotation. When this synchronization is disrupted by jet lag or by staring at bright screens late at night, your internal clocks become desynchronized, leading to fatigue and a general feeling of being off. We now know that physical time, relativity, is flexible, and biological time, SCN, is cyclic. But there is a third kind of time, subjective time, or the way you feel time passing. You know this feeling well. When you're engaged in a deeply enjoyable activity, time seems to vanish. Hours pass without notice. Conversely, when you are bored, waiting in line, or under stress, seconds can feel like they stretch endlessly. Objective time, the time on your wall clock, remains steady. It is your perception of time that changes. This is not just a psychological trick. It is driven by your brain chemistry. For example, when you're excited or in danger, your brain releases neurochemicals like adrenaline and dopamine. These chemicals increase your awareness and your sensory processing speed. As your brain records more information in a short period, it can create the illusion that the event lasted longer than it objectively did. It's like your brain is recording at a higher frame rate. Conversely, routines, boredom, and lack of strong sensory input lead to a lower perceived rate of information flow, causing time to feel compressed or uneventful. Time is also deeply connected to memory. Your brain does not store memories with a date and timestamp like a calendar. It stores memories based on meaning and emotional impact. A childhood summer may feel long because it was filled with novel experiences, while a recent, monotonous year might feel short because it lacked distinguishing moments. Your feeling of time is therefore a story written not by light, but by attention and novelty. We began this journey by exploring the incredible speed of light, and now rest on the quiet rhythm of the human heart. To unify these threads, we recognize that time exists on three interwoven levels. There is physical time, which is relative, constantly bending due to motion and gravity, simply to maintain the universe's absolute speed limit. Then there is biological time, the complex, internal clockwork orchestrated by the suprachiasmatic nucleus, which uses the very light hitting your eyes to synchronize every cell and organ in your body. Finally, there is subjective time, which is personal and fluid, where the seconds are stretched or compressed, not by physics, but by the neurochemistry of your emotions and level of engagement. You are never truly separate from time. You are built from the rhythm of light, the physical geometry that defines all motion, and you live by the rhythm of light, the biological cycle that governs your sleep and waking. Even as you are still, lying here in the quiet, the atoms inside you are flickering in a rhythm set by the quantum world. The space you occupy is slightly different in terms of gravity and time from the space outside your room. You carry time with you. It is personal and flexible. Tonight, as you look up at the stars, you are witnessing light that has traversed millions of years. Light that, from its own perspective, crossed the distance instantly. And that ancient light, upon striking your retina, will help regulate the cycle that determines when you sleep and wake tomorrow. You are the meeting point of cosmic time and biological time. You are time's keeper, and time is your constant companion. Before the precision of mechanical gears and digital displays, humanity understood time as a natural, cosmic rhythm dictated by light and shadow. Time was not a sequence of fixed minutes. It was the slow, predictable movement of the sun and stars across the sky. Early cultures mastered this natural timing using simple observation. The first scientific instrument for measuring time was the gnomon, essentially a straight stick placed vertically into the ground. As the sun followed its path, the shadow cast by the gnomon tracked the day's progression. This simple device, the original sundial, translated the sun's motion into a quantifiable language. It allowed early societies to synchronize activities, knowing precisely when to start the harvest, when to gather, and when to rest based on the sun's position, thereby establishing fundamental societal structures tied directly to astronomical cycles. When the sun set, the celestial clocks took over. Our ancestors realized that the patterns of constellations rotated predictably, not just nightly, but seasonally. The appearance or disappearance of star groups acted as vast, reliable calendars. For example, the rising of the star, Sirius, often called the dog star, was critically important to ancient Egyptians, as it closely preceded the annual flooding of the Nile River, signaling the start of the farming season. This alignment of human life with celestial mechanics required monumental effort. Great architectural structures like Stonehenge in England or Chichen Itza in Mexico were not built merely for ceremony. They functioned as immense, stationary, astronomical instruments. These structures were precisely engineered to align with the sun's position during the solstices or equinoxes. They proved that ancient peoples possessed a deep, functional understanding of orbital mechanics and the constant relationship between light, shadow, and terrestrial time. The legacy of these celestial timekeepers continues to define modern standards. Today, astronomers use the extremely precise transit of stars, the exact moment a star crosses the meridian, to define the length of a single day with unparalleled accuracy. Furthermore, modern atomic clocks, the most accurate timekeepers in existence, are calibrated using the precise frequencies of light pulses. And space agencies, rather than relying on internal mechanisms, track Earth's rotation by observing the reflection of sunlight off satellites. Every modern measurement of time, therefore, remains inextricably linked to the ancient, simple, yet absolute movement of light. The idea that time was universal and absolute remained the bedrock of physics for centuries, largely unchanged since Isaac Newton's era. However, this concept proved incompatible with a critical observation about light. The experimental fact is that light always travels at the same speed, regardless of the observer's motion. If you shoot a flashlight while moving in a high-speed train, the light beam moves away from you at the same speed as if you were standing still. The speed of light is 299,792,458 meters per second, a value that is truly constant. Albert Einstein recognized that if this speed is a fixed constant, then the other components of reality, time and space, must be flexible. This radical idea formed the basis of his special theory of relativity, 1905. If two observers in relative motion measure the light traveling between them, and they both must arrive at the same speed, their measurements of the distance traveled and the time elapsed must be different. The consequence of this necessary adjustment is time dilation. For an observer in motion relative to a stationary point, time physically slows down. the moving observer will experience a shorter duration for the same event than the stationary observer does. The faster the motion, the more pronounced the time difference. This effect is not just theoretical. It has been proven repeatedly in physics laboratories using elementary particles. For instance, subatomic particles, called muons, are created when cosmic rays strike the atmosphere. Muons have an extremely short lifespan of just 2.2 millionths of a second before they decay. If time were absolute, they would decay before reaching the Earth's surface. However, due to their high velocity, their internal clock is slowed down relative to us, time dilation, allowing many of them to survive the journey and reach the ground, a direct, daily confirmation of special relativity. Einstein's breakthrough didn't stop with motion. His general theory of relativity, 1915, revealed that gravity is also a relativistic effect that dictates the flow of time. To understand this, Einstein proposed a unified field he called space-time. This concept merges the three dimensions of space: up, down, left, right, forward, backward, with the one dimension of time into a single, integrated, four-dimensional structure. Gravity is not a mysterious force reaching out across the void. Instead, gravity is the curvature of space-time itself. Imagine a tightly stretched, invisible sheet representing space-time. When an object with mass like the sun, a planet, or even a human rests on this sheet, it creates a dip or a warp. Any nearby object, including light, doesn't travel in a straight line. It follows the curve of the space-time created by the mass. The Earth orbits the Sun because it is simply following the slope of the depression the Sun created, much like a marble rolling around a funnel. Because time is fused with space in this fabric, any mass that curves space also warps time. This phenomenon is gravitational time dilation. The stronger the gravitational field, the deeper the space-time curve, the slower time flows, and the weaker the gravitational field, further from the mass, the faster time flows. This effect is incredibly precise and measurable. Scientists have demonstrated this by comparing two atomic clocks, one placed at ground level and one placed just 1 foot, or roughly 30 centimeters higher. The clock placed higher, where the Earth's gravity is marginally weaker, was measured to tick faster than the lower clock. The difference is minuscule, about 1 trillionth of a second, but it is absolute physical proof that time is not uniform across the planet. The most immediate, real-world application of both forms of time dilation is the Global Positioning System, GPS. The system relies on satellites orbiting the Earth at an altitude of approximately 20,000 kilometers and a speed of about 14,000 kilometers per hour. Engineers must perform constant daily corrections for the Global Positioning System due to two opposing relativistic effects. The satellite's high velocity, covered by special relativity, causes their clocks to tick slower than clocks on the ground by about 7 microseconds per day. However, their location far from Earth's gravitational center, covered by general relativity, causes their clocks to tick faster by approximately 45 microseconds per day. The combined net effect is that the satellite clocks run about 38 microseconds, or 38 millionths of a second, faster each day. If these adjustments were not made, the timing errors would quickly compound, and your phone's GPS application would calculate your position incorrectly, leading to an error of several kilometers within hours. Every time you use your navigation app, you are relying on the fundamental reality that time is flexible and dependent on motion and gravity. The ultimate thought experiment to illustrate the reality of time as a non-absolute quantity is the twin paradox. Imagine two identical twins, twin A and twin B. Twin A remains on Earth in a relatively stationary reference frame. Twin B boards a high-speed spacecraft and travels on a long round trip into deep space at a constant velocity approaching the speed of light, say 99% of light speed. From the perspective of twin A on Earth, twin B is moving extremely fast. Due to time dilation, twin A observes twin B's clock, heart rate, and biological processes running significantly slower than their own. From the perspective of twin B on the spacecraft, time appears to be normal inside their ship. Their clock ticks normally. They age normally. However, the external universe appears to be distorted. Space ahead of them is contracted, Lorentz contraction, making their journey shorter than it appears to twin A. When twin B returns to Earth, the result is the paradox. Twin A has aged decades, while twin B has only aged a few years. The resolution lies in the fact that it is not truly a paradox. It is a consequence of the universe's geometry. Twin B is the one who experienced acceleration and deceleration, changes in velocity required to leave and return to Earth. This change in their inertial reference frame is what breaks the symmetry between the twins, confirming that the traveler's experience of time was genuinely shorter. The twin paradox confirms that time is not a shared cosmic constant. It is personal. It is shaped by the unique path you take through the four-dimensional space-time fabric. Even in our daily lives, this principle holds true. Your motion across the Earth, the elevation of your desk versus your feet, and the speed of the planet's rotation all contribute to your singular, individualized experience of time's flow. Your time is truly your own. We have explored how motion and gravity subtly shape our personal timeline. Now, let's consider what happens when motion is no longer subtle, but approaches the ultimate cosmic speed limit. What would it truly mean to travel at 99.999% of light speed? For an observer watching this extreme velocity from a stationary position, the effects of time dilation are no longer subtle. They are immense. The traveler's clock would appear to tick agonizingly slow. Years might pass on Earth, while the traveler perceives only days or weeks. If the traveler were to look out at the cosmos, the history of galaxies would unfold in a blur. Stars aging, planets orbiting, and entire civilizations rising and falling in what seems like fast-forward motion. The traveler is essentially accelerating through space at such a rate that their progress through time is drastically minimized. This phenomenon is why physicists consider motion to be a pathway through time itself. The faster one commits to a direction in space, the slower they must proceed through the temporal dimension. The sheer mathematical scale of this distortion is difficult to grasp, but it is a genuine, measurable consequence of the universe's geometry. However, from the perspective of the traveler inside the spacecraft, nothing feels unusual. Their heart rate, their internal biological clocks, and the mechanical clock on their wall all function at their normal pace. Time dilation is inherently relative. The stretching of time is only apparent when comparing two different frames of reference. For the traveler, their second remains exactly 1 second long. This lack of perceived change within their own reference frame is a critical concept in relativity, confirming that the laws of physics, including the flow of time within their vessel, are upheld equally, regardless of the speed. This near-light speed journey would allow the traveler to traverse the galaxy in a single human lifetime. crossing distances that would take the stationary observer tens of thousands of years. This extreme time difference is not a technological malfunction. It is the physical mechanism by which the universe ensures the speed of light remains constant for everyone, everywhere. This relationship between velocity and time is defined by the Lorentz transformation, an equation that quantifies exactly how much time must stretch to keep light's speed absolute across frames of reference. Despite the possibility of approaching the speed of light, one absolute law remains. Nothing with mass can ever truly reach the speed of light, which is represented by the variable c. Light itself, the photon, is able to travel at this speed because it is massless, meaning it has zero rest mass. But for any object that possesses mass, a spacecraft, a planet, or even a single atom, the rules of relativity impose a strict, physical barrier. The reason lies in the fundamental relationship between mass, energy, and velocity. As an object accelerates and its velocity increases, its relativistic mass also increases. This effect is a direct consequence of the famous equation proposed by Einstein, which states that energy equals mass times c squared. To describe this simply, mass and energy are fundamentally interchangeable and are proportional to one another by the square of the speed of light. As a massive object approaches the speed of light, its mass approaches infinity. Therefore, to push the object from near light speed to the exact speed of light, an infinite amount of energy would be required. Since an infinite energy source does not exist, the speed of light acts as an insurmountable cosmic boundary. It is impossible to accelerate beyond this limit because the energy input required becomes astronomically large. Even modern particle accelerators, which move protons and electrons to 99.99999% of light speed, require vast amounts of energy to nudge them that final, infinitesimal fraction closer. This boundary is not a matter of poor engineering or insufficient fuel. It is a geometrical constraint written into the structure of space-time. It prevents the universe from descending into mathematical paradoxes, ensuring that the rules of cause and effect remain intact. This boundary prevents any massive object from ever experiencing the point where time stops entirely, reserving that singular timeless existence only for the photon. The principles of relativity are not confined to thought experiments involving infinite energy or distant galaxies. They are a necessary component of our daily lives, particularly in the function of the Global Positioning System, GPS. The GPS network consists of approximately 31 satellites orbiting the Earth at an altitude of about 20,200 kilometers. Each satellite carries an array of ultra-precise atomic clocks, which are essential because the GPS determines your location on Earth by measuring the exact time it takes for a signal to travel from at least 4 different satellites. To calculate distance precisely, the clocks must be accurate to within 20 to 30 nanoseconds, or billionths of a second. However, scientists discovered a profound problem. The highly precise clocks aboard the satellites do not keep time with clocks on Earth. They run too fast. This discrepancy reveals the necessity of applying both special and general relativity. The clocks in orbit are subject to 2 powerful and opposing relativistic effects, which must both be quantified and corrected. The first effect is dictated by special relativity, which deals with velocity. Since the satellites move at an enormous orbital speed, approximately 14,000 kilometers per hour, they experience time dilation. Due to this high velocity, the satellite clocks run slower than ground clocks by about 7 microseconds, or 7/millionths of a second per day. This principle is identical to the one that causes the twin paradox, confirming that increased speed causes a demonstrable slowing of time. The second, and more dominant, effect is dictated by general relativity, which deals with gravity. The satellites are far from Earth's center, meaning they experience significantly weaker gravity than clocks on the ground. According to general relativity, the weaker the gravitational field, the faster time flows. Consequently, this difference in gravity speeds up the satellite clocks by about 45 microseconds, or 45 millionths of a second, per day relative to Earth. The final, net result is the difference between these two powerful effects. The speeding up caused by the weak gravity outweighs the slowing down caused by the high velocity. The calculation is straightforward. The time gained from weak gravity, 45 microseconds, minus the time lost from high speed, 7 microseconds, results in a net gain of approximately 38 microseconds per day. For GPS to function correctly, this timing error must be accounted for. If the satellite clocks were left uncorrected, the timing drift would quickly accumulate. Because signals from the satellites travel at the speed of light, a 38 microsecond error translates to a distance error of approximately 10 kilometers within just one day. The system would be completely useless for accurate navigation. To solve this, the GPS engineers utilize Einstein's equations to make a precise adjustment. Before the atomic clocks are even launched into space, their internal frequency is pre-corrected or slowed down so that once they are subjected to the relativistic effects in orbit, they will effectively tick at the exact same rate as clocks on Earth. This quiet, continuous adjustment is one of the most powerful and necessary proofs of relativity. Every time you check the map on your mobile device, you are leveraging the fact that time is flexible, personal, and continuously bent by the forces of motion and gravity. The physics conceived in thought experiments over a century ago is now a fundamental, non-negotiable component of our daily technology. We have confirmed that time is relative, shaped by the geometry of space-time. Now, let's shift our perspective to view time not as a duration, but as an actual map of the universe, a map drawn entirely by light. When we observe the night sky, we are not looking at a static photograph of the cosmos as it is now, but rather a mosaic of historical events. Every beam of light we receive from a distant celestial body serves as both a measure of distance and a record of time. This unique property allows astronomers to effectively use light as a combined coordinate system for space and time. Within our immediate solar neighborhood, the time lag for light transmission provides clear examples of the vast distances involved. Light traveling from the moon reaches our eyes in just over 1 second. Expanding that distance, the light leaving the surface of the sun takes approximately 8 minutes and 20 seconds to warm the Earth. Looking outward to the gas giants, light originating from Jupiter requires between 33 and 52 minutes to arrive. The exact duration varying significantly based on the dynamic alignment of the two planets in their orbits. Each of these time lags places us slightly in the past relative to the object we observe. Stretch this concept further. The light arriving from the Andromeda Galaxy, our nearest galactic neighbor, began its journey 2.5 million years ago. That means we are seeing Andromeda as it appeared when early human ancestors first began walking the Earth. This merging of time and distance leads to the scientific measurement known as the light year. It is crucial to remember that a light year is primarily a unit of distance, defined as the enormous distance light travels in one Earth year, roughly 9,500 billion kilometers. When astronomers state that a star is 1,000 light-years away, they are also stating that the light we see tonight left that star 1 millennium ago. This cosmic light map is why observation is inherently an act of looking backward in time. Telescopes are not just devices for magnification. They are time machines that allow us to witness the universe in various stages of its development. The stars we observe are seen as they were, not as they currently are. For example, the spectacular cloud of gas and dust, known as the Crab Nebula, is located approximately 6,500 light-years from Earth. We observe the remnants of a powerful supernova that occurred over 6 millennia ago. Should that star have gone dark, faded, or changed its state drastically yesterday, we would remain unaware for another 6,500 years. This realization is fundamental to cosmology. When scientists observe extremely distant objects, such as the earliest galaxies forming shortly after the Big Bang, they are seeing light that has traveled for over 13 billion years. They are literally witnessing the universe in its infancy. Thus, the light that reaches us is a message in a bottle, a history written in energy, detailing the expansion, evolution, and eventual fate of celestial bodies. Every point of light, no matter how faint, is a recorded memory of the universe's past. We have established that light carries time, allowing us to map the universe's history. Now, we must confront the ultimate paradox. What happens to time when you are the light itself? We know from the principle of relativity that objects with mass are physically unable to reach the speed of light. However, we can use the photon, the particle of light, as a thought experiment to understand the limit of temporal experience. Imagine, hypothetically, that you become a photon, released from the core of a star. You possess zero rest mass and immediately accelerate to the absolute cosmic limit of nearly 300,000 kilometers per second. The fundamental rule of relativity states that as motion approaches c, time dilation becomes extreme. At the exact speed of light, the mathematical equations of relativity reveal that the passage of time for the photon literally becomes zero. From your perspective as a photon, your existence is timeless. The moment you are generated in the fiery heart of the star, you simultaneously arrive at your destination, whether that destination is a distant galaxy or a lens on Earth. The vast distance, perhaps billions of light years, is contracted entirely. You do not experience any duration, no before, no after, and no passing seconds. The source and the destination touch instantaneously. This is the most extreme form of stillness possible in the universe. Time does not merely slow down for the photon, it stops completely. This discovery presents a profound paradox. The very mechanism that defines and carries the flow of time throughout the entire universe is itself immune to time. Light operates outside of duration. To an astronomer on Earth, the journey of a photon takes billions of years, allowing them to measure cosmic history. But to the photon, that journey takes zero time. This difference in experience is the clearest possible illustration that time is not an external, universal measure, but is entirely dependent on the frame of reference. Furthermore, humanity relies on light to measure the very thing it does not experience. Our most precise atomic clocks measure time by counting the vibrations of photons, the transition frequencies of atoms like cesium. In essence, we measure the passage of our own chronological existence by observing the rhythm of a particle that is fundamentally timeless. This reveals that light is not just a form of energy, it is the defining constant of reality. It sets the limit of speed, shapes the curvature of space-time, and dictates the pace at which all events, from the decay of a muon to the orbit of a galaxy, unfold. You cannot escape time, but light does. And by carrying the memory of the past instantly to your present, light connects your human experience to the history of the entire universe. The speed of light, denoted by c, is more than just a velocity measurement. It serves as the governing constraint that gives structure and consistency to the universe. This boundary dictates the limits of physics, causality, and connectivity. The fundamental law of physics is that information cannot travel faster than light. This limit ensures causality, the principle that a cause must always precede its effect. Without the absolute speed limit, every event in the universe could potentially influence every other event simultaneously, leading to a state of physical chaos where the order of events becomes meaningless. Due to this constraint, everything in the cosmos is governed by the beat of light's speed. Even phenomena that seem outside the electromagnetic spectrum, such as gravitational waves, ripples in the fabric of space-time itself, have been measured to travel at the speed of light. Our entire observable reality is synchronized to this singular, unyielding tempo. Because we are massive objects, this limit binds us to a certain experience of time. We are prevented from skipping ahead or looping back into the past. We are constrained to a one-directional, relatively slow path through time. Yet, light, the timeless messenger, continuously delivers the past to our present every time we look up. The beams surrounding us carry echoes, some only minutes old, others millions of years old, bringing historical data instantly from their perspective, only to be received and processed in our time-bound reality. To fully grasp the boundary set by light, we must return to the physics of the photon. A photon is a unique entity because it is massless. This is the key physical property that allows it to move exactly at the speed of light. For a photon, the mathematical consequences of special relativity are absolute. At velocity c, the passage of time is zero. This means that for a photon, the entire universe undergoes extreme spatial contraction and temporal cessation. The moment a photon is emitted, say, from a distant quasar, is the exact same moment, in the photon's own frame of reference, that it is absorbed, perhaps by a detector on Earth, billions of light years later. The photon functions not as an object on a journey, but as an instantaneous link, or a bridge, between its origin and destination. It is a profound truth of physics. Light exists outside of time's flow. It does not age, its energy does not diminish due to duration, and it carries no memory of the journey. Yet, it travels through a universe defined entirely by clocks, setting the pace for all other forms of existence. This creates the fundamental paradox of time measurement. Light is the timeless entity that defines time for everything else. All of our most precise standards for time down to the atomic level are calibrated by counting the transition frequencies of photons within specific atoms. We rely on the rhythm of a particle that itself possesses no rhythm. We use light to measure what it does not experience, trusting it to carry the history of the stars even though it never ages. This challenge to intuition forces us to view time not as an independent, universal stream, but as a relationship, a connection between objects that move slowly and those that move at the absolute maximum speed. the human experience is anchored firmly within time, while the light we observe exists only in the stillness of its movement. To fully understand how time and light interact, we must recognize their inseparable nature within space-time. Space-time is not an abstract concept. It is the unified four-dimensional reality that combines the three dimensions of space with the single dimension of time. These four dimensions are woven together into a single, cohesive, dynamic structure. There is no such thing as being purely in space or purely in time. All objects are moving through space-time simultaneously. General relativity describes how mass interacts with this fabric. Instead of being a passive stage, space-time is dynamic and responsive. When massive objects, stars, planets, or black holes are present, they cause the surrounding fabric to curve or warp. This curvature is the physical manifestation of gravity. This dynamic structure is also capable of vibration. When extreme cosmic events occur, such as the merger of two black holes, the immense rearrangement of mass sends out gravitational waves, ripples in the fabric of space-time. These waves travel outward at the speed of light, bending time and space momentarily as they pass through, providing another powerful confirmation of the fabric's responsive, unified nature. To track motion within this four-dimensional reality, physicists use the concept of a world line. A world line is the unique path or trajectory of an object through space-time. Every single entity, from a photon to a planet, traces its own world line. The crucial insight here is that all objects are always moving through space-time. Even when you are lying perfectly still, you are moving forward along the time axis. Your world line is being drawn by the steady, forward flow of time. This constant motion through the temporal dimension means that your path through space-time is never perfectly straight. The presence of massive objects nearby, like the Earth, creates a gravitational curve. You are constantly following this curve, which is why objects appear to fall to the ground. Gravity is simply the gentle, continuous curve of your world line as you move through space-time. You are not being pulled down by a force. You are merely following the natural, curved shape of the environment dictated by mass. Because time and space are unified, any movement we make in the spatial dimensions affects our rate of movement in the time dimension, time dilation. Conversely, the curve imposed by mass, gravity, affects our world line, causing time to flow differently, gravitational time dilation. Our existence is a continuous glide along a world line determined by the combined shape of space-time, ensuring that every moment, every movement, and every second is a unique, precise event within the cosmic framework. We have explored how the fabric of space-time is gently warped by mass and motion. We now turn to the most extreme manifestation of this warping, the black hole, a region where gravity has intensified to the point that it dictates the ultimate fate of time. A black hole is the spectacular, yet inevitable, result of the gravitational collapse of massive stars. When a star exhausts its nuclear fuel, the immense outward pressure generated by fusion can no longer counteract the inward pull of gravity. The star collapses into an object of unimaginably small volume and colossal density, forming a singularity, a point where the space-time curvature becomes mathematically infinite. The surrounding region of no return is called the event horizon, the boundary beyond which the escape velocity exceeds the speed of light. This is the ultimate physical boundary in the universe. Beyond this line, no signal, no matter, and most critically, no information can ever return to the external cosmos. Here, time begins to exhibit its most dramatic relativistic effects, creating a profound discrepancy between the internal and external experience. Imagine an observer orbiting the black hole at a safe distance. This observer watches a spacecraft containing a powerful clock and radio transmitter slowly descending toward the event horizon. To the crew inside the descending spacecraft, their internal clock ticks normally, and the laws of physics appear unchanged. They cross the event horizon without feeling any immediate, localized boundary or jolt. However, for the external observer, a bizarre, physically real phenomenon unfolds. As the spacecraft gets closer to the massive gravity well, its light signals must fight harder and harder to climb out to the distant observer. This extreme gravitational resistance causes the signals to lose energy, resulting in a pronounced gravitational redshift. The light is stretched toward longer, redder wavelengths. This redshift continues until the light is stretched into invisibility, falling below the detectable range. More critically, the external observer sees the spacecraft's clock begin to slow down dramatically. The seconds marked by the descending clock stretch into minutes, then hours, for the distant observer. This is because the massive concentration of energy and mass in the singularity is bending the time dimension itself. As the spacecraft approaches the event horizon, its time appears to slow to a crawl, and the spacecraft and its light signals appear to become frozen permanently at the boundary, never truly crossing it from the external perspective. This extreme gravitational time dilation means that near the horizon, time itself is nearly stationary relative to the outside universe. Black holes are not merely cosmic destroyers. They serve as critical laboratories for general relativity, confirming that time is deeply plastic and responsive to mass. They underscore that time is not a single tempo shared by everyone. Even our own galaxy, the Milky Way, is anchored by a supermassive black hole at its center, named Sagittarius A star. This immense object, with a mass equal to about 4 million times the mass of our Sun, dictates the gravitational choreography of billions of stars orbiting it. The existence and properties of Sagittarius A star confirm that these extreme gravitational wells are fundamental, stable structures in the cosmos. Observations of stars orbiting Sagittarius A star at high velocity provide the most direct evidence that general relativity accurately predicts extreme gravitational effects, even though these stars are still thousands of times the black hole's radius away. The black hole challenges our intuitive understanding of time because the moment an object crosses the event horizon, the relationship between space and time literally flips. Outside the horizon, movement in space is optional, but movement in time is mandatory. We must move forward in time. Inside, the direction forward in space is mandatory, toward the singularity, and the roles are reversed. Escaping becomes physically impossible. It would require moving backward in time, which is not permitted. The singularity is the inevitable, singular destiny of everything that falls across the threshold. The extreme effects near a black hole highlight a reality that affects us constantly, albeit minutely. There is no single, shared, universal now. In everyday life, we operate under the practical assumption that if two people look at their watches and see 3 o'clock, they are experiencing the exact same moment. However, relativity proves this is physically inaccurate. Your now and another person's now are always slightly out of sync due to differences in their individual world lines, their unique paths through space-time. Even two people standing in the same room are slightly desynchronized. For example, the clocks in your body are affected by the Earth's gravity. The part of your body that is higher up your head experiences a minuscule difference in gravitational pull compared to your feet. Consequently, the time elapsed for your head is ever so slightly longer than the time elapsed for your feet. This difference, although only a fraction of a second over a lifetime, is real, measurable, and confirms that time is inherently personal. This difference is compounded by motion. While the Earth is rotating and orbiting the Sun, every person on Earth is moving at a different velocity relative to every other person. A person standing on the equator is moving faster than a person standing near the North Pole. A person on a high-speed train is moving faster than someone standing on the platform. These minute velocity differences ensure that the time dilation experienced by each person is unique. This means that every individual carries their own unique temporal rhythm dictated by their accumulated velocity, altitude, and proximity to mass. If time is so highly individualized, how do human societies manage to coordinate complex events like air travel, financial transactions, and communication networks? The answer is that human civilization functions based on an agreed-upon structure, the social clock. We have collectively agreed to ignore the minuscule relativistic differences and adopt a standardized measure: the second, the hour, the calendar. This shared clock is maintained and distributed by highly stable systems, such as the GPS time signal, corrected for relativity, and the International Atomic Time scale. This agreement is a triumph of engineering over physics. Financial markets, for instance, must synchronize transactions down to the nanosecond, 1/billionth of a second. Power grids must synchronize their alternating current cycles. These systems rely entirely on the fact that scientists have used the equations of relativity to calculate the necessary corrections to bring all the world's clocks into functional harmony. Our ability to coordinate is based not on absolute time, but on consistent, mathematically corrected agreement. The social reality of a shared now is a carefully constructed synchronization built upon the underlying physical reality that time is always personal and relative. The principle of time dilation that drives black hole physics and individual time differences can be elegantly demonstrated using the light clock thought experiment. This clock is the ideal ruler for understanding time because its core mechanism relies solely on light's constant speed. The light clock is purely conceptual, constructed with only two parallel mirrors separated by a fixed distance, with a single photon bouncing vertically between them. Each complete round trip of the photon defines one tick of time. Since the speed of light is constant, the time interval between ticks is perfectly reliable based on the fundamental physics. Time equals distance divided by speed. Now, imagine this light clock is placed on a high-speed vehicle moving horizontally at a constant velocity. From the perspective of a stationary observer watching the clock move, the photon does not travel straight up and down. Instead, it traces a longer, diagonal path up, over, and down, because the mirrors are shifting horizontally while the photon travels vertically. Since the fundamental rule of the universe dictates that the speed of light must remain the same for all observers, and the diagonal path is demonstrably longer than the stationary vertical path, the time taken for the light to complete one tick must be longer. Therefore, The stationary observer sees the moving light clock ticking slower than their own stationary clock. This is the conceptual proof of time dilation. The amount by which time stretches can be precisely calculated using the Pythagorean theorem a squared plus b squared equals c squared, applied to the space-time geometry, which yields the Lorentz transformation. The light clock confirms that time is not an independent constant, but a variable dimension integrated with space. When motion forces the light to travel a longer distance, time itself must expand to ensure the constant speed of light remains the governing law. It demonstrates that motion through space requires a necessary reduction in motion through time. We return to the concept of extreme motion, exploring the profound consequences of accelerating a massive object to near the speed of light. This journey reveals a critical cosmic constraint known as the fixed motion budget built into space-time. Imagine you are in a spacecraft accelerating smoothly and silently through the dark vacuum of space. As your velocity increases towards the speed of light, the time you experience begins to stretch relative to a stationary observer. This occurs because the universe imposes a limit on your overall motion through the 4 dimensions of space-time. You cannot spend your motion budget freely. The total movement must be divided between the spatial dimensions and the temporal dimension. This fundamental trade-off is mathematically derived from the structure of the universe. You have a fixed motion budget in space-time. If you move slowly through space, like being relatively stationary on Earth, you dedicate nearly all of that budget to advancing quickly along the time axis. Conversely, if you move quickly through space, at speeds approaching light, you must divert a significant portion of that budget, forcing you to move slowly along the time axis. At velocities reaching 99.9% of light speed, the effect is no longer subtle. A day experienced inside the spacecraft could correspond to a year passing on Earth. This is not a malfunction or an illusion. It is the physical mechanism of time dilation, ensuring that the fundamental law, the speed of light is constant, remains consistent across both frames of reference. From the traveler's perspective, there is no discomfort or change in their internal tempo. Their heartbeat, their thoughts, and their clock all slow down together. The perception of time remains normal within the moving system. However, the consequence is clear. A journey of only a few years for the traveler could result in a return to an Earth that has aged centuries, a true form of one-way time travel achieved purely through high-speed motion. This effect, though minor in common experience, is measured and confirmed on a daily basis. Astronauts aboard the International Space Station, moving at over 27,000 kilometers per hour, age fractions of a second less than their counterparts on Earth. The faster you move, the thinner your timeline becomes. To understand the magnitude, consider the example of muons. These subatomic particles are generated high in the Earth's atmosphere. Muons have an extremely short, natural half-life of about 2.2 microseconds, 2.2 millionths of a second. Based on their half-life and the distance to the Earth's surface, almost none should survive the journey. However, because these muons travel at speeds close to light, time dilation occurs. Their internal clock slows down relative to our frame of reference. This allows a significant number of muons to reach the ground before their half-life has elapsed, providing a constant, tangible confirmation of special relativity. This scientific reality validates the notion that time is indeed a variable dimension, adapting to the velocity of the observer. We now transition from the time-bending effects of high velocity to the subtle, ever-present influence of gravity. The connection between motion and gravity is unified by Einstein's foundational principle of equivalence. This principle states that the effects of a uniform gravitational field are physically indistinguishable from the effects of uniform acceleration. A classic thought experiment illustrates this. A person inside a windowless elevator cannot tell the difference between standing still on Earth, experiencing gravity, and accelerating uniformly upward in space, experiencing inertia, mimicking gravity. This indistinguishability led Einstein to the revolutionary conclusion that gravity is not a force, but a geometrical distortion of space-time. This perspective radically changes the meaning of falling. When an object, such as a feather or a stone, falls toward the Earth, it is not being pulled by an invisible force in the traditional sense. Instead, because the Earth's mass has curved the surrounding space-time fabric, the falling object is simply following the most natural, straightest path available to it within that curved geometry. The feather's graceful descent is its attempt to follow the geodesic, the shortest path of the curved space-time, toward the Earth's center. This demonstrates that all objects, regardless of mass, fall with the same acceleration precisely because they are all following the same curvature of the four-dimensional world line. Gravity, therefore, not only bends the spatial dimensions but also creates a temporal gradient. The closer an object is to the center of Earth's mass, the stronger the gravitational pull and the slower time flows. This subtle difference in time flow across a single body is known as the tidal effect on time. This is why the clocks on your feet tick slightly slower than the clocks near your head. The difference is microscopic, but it is a real physical consequence of this gravitational gradient. The descent of the feather is not merely influenced by air resistance. Its path is guided through layers of slightly differing time rates. As it falls, it is gliding through a region where time flows progressively slower, demonstrating that even the most gentle motion on Earth is a continuous, subtle interaction with the curvature of time. This principle underscores the fact that the concept of a universal now is a social construct, not a physical reality. Due to the gravitational gradient, even people standing side by side do not share the exact same moment. The person standing closer to the Earth's core experiences time marginally slower than the person standing farther away. Furthermore, slight differences in velocity, even on Earth, ensure individual time streams are never perfectly synchronized. A person living at sea level and frequently flying east-west experiences a different accumulated time than a person living at a high altitude and rarely moving. These minute velocity differences ensure that the time dilation experienced by each person is unique. This means that every individual carries their own unique temporal rhythm, dictated by their accumulated velocity, altitude, and proximity to mass. This physical reality is ignored in daily life, but it is constantly corrected for in technologies requiring extreme precision, such as GPS synchronization and high-frequency trading platforms. While physics defines time by the motion of light and the curve of gravity, the human brain processes time according to an entirely different, highly flexible rhythm. We explore the remarkable volume of information contained within a single subjective second of consciousness. A physical second, defined by atomic oscillation, is an immutable duration. However, the brain's internal processing speed transforms that fraction into a complex, integrated experience. Consider the chain of events required to experience a single visual perception. In less than a billionth of a second, a photon enters the eye and is captured by photoreceptors on the retina. These receptors instantly convert the light into a chemical signal, which triggers an electrical pulse, a neural action potential. This pulse travels along the optic nerve to the visual cortex in the back of the brain. Before half a second has elapsed, the brain has already begun to reconstruct the image, a process that involves billions of synaptic firings. Simultaneously, for auditory input, vibrations entering the ear are translated into mechanical waves, converted into fluid movement in the cochlea, and then transduced by hair cells into electrical signals. Both visual and auditory pulses must be synchronized by the brain to form a coherent, unified moment of now. This synchronization is essential for causality in our perception, ensuring that we correctly attribute the sound of thunder to the sight of lightning. Despite the speed difference between light and sound waves, the true depth of a single second lies in the integration of sensory data with memory and emotion. After basic sensory input reaches the appropriate cortical areas, key brain regions immediately engage. The hippocampus compares the incoming information to existing memories for context and novelty. The amygdala filters the moment based on emotional relevance, like danger or pleasure, assigning a survival priority, and the prefrontal cortex directs attention and consciously processes the event's meaning, generating a cognitive response. In this single second, billions of neurons fire in a silent, complex symphony, compiling raw input into awareness. The brain does not simply record time, it creates time by stitching these moments of integrated awareness together, generating the continuous narrative of consciousness. Every choice, every recognition, and every feeling is generated through this intense neural choreography occurring in fractions of a second. This internal processing speed explains why our perception of time is so flexible, a phenomenon known as temporal dilation of experience. Physical time remains constant, but the speed at which the brain processes information is highly variable and dictated by neurochemistry. In moments of intense stress, danger, or profound joy, the brain releases powerful neurochemicals like adrenaline and dopamine. These chemicals sharpen focus, increase sensory input, and accelerate the rate at which details are recorded and stored. Because the brain records more detailed information into memory during a critical event, when the event is played back or recalled, it feels as though it lasted much longer than the objective clock time. The brain's subjective time effectively stretched, allowing a single second to contain the depth and complexity of many. Conversely, during periods of boredom or routine, the brain processes less novel information, causing time to subjectively compress and feel as though it is rushing by. This proves that the biological experience of time is tied directly to the salience and novelty of events, rather than external clock mechanisms. The human experience of time is thus a continuous negotiation between the immutable laws of physics that govern the universe and the flexible, chemically mediated processing speed of our own consciousness. We venture to the origin of time itself, moving beyond our conventional systems of measurement to the moment that birthed the universe. The genesis of time is inseparable from the genesis of all matter and energy, an event known as the Big Bang. The physical event was not an explosion in space, but rather a catastrophic, instantaneous expansion of space itself. In that initial hyper-dense, hyper-hot state, the concepts of space, time, and matter as we know them were unified. Before this expansion, The concept of before is physically meaningless, as time, defined by change, had not yet begun its flow. Time is, fundamentally, the measure of change. As soon as the universe began to change its density, temperature, and configuration, the ticking of the cosmic clock commenced. The initial second of the universe's existence was a moment of furious, radiant chaos. The temperature was estimated to be around 10 to the power of 32 degrees Celsius, a temperature at which the four fundamental forces of nature were unified into a single force. The most dramatic event within this early period was the inflationary epoch. This occurred in the first 100 trillionth of a trillionth of a trillionth of a second. During this period, the universe underwent exponential expansion, doubling in size hundreds of times in an instant. This rapid inflation is vital to modern cosmology, as it explains why the universe appears so smooth and uniform today. It stretched the tiny quantum fluctuations into the large-scale structures we observe, and it solidified the fundamental properties of spacetime. Following inflation, the universe continued to cool, leading to a sequence of fundamental events that defined reality. During the electroweak epoch, at approximately 10 to the power of minus 12 seconds, the electromagnetic force and the weak nuclear force separated, marking the full establishment of the four distinct forces we observe today. Around this same time, the crucial process of baryogenesis occurred, while the exact mechanism remains a complex mystery. A slight asymmetry between matter and antimatter resulted in one particle of matter remaining for every billion pairs that annihilated. This imbalance is the fundamental reason the universe today consists almost entirely of matter, enabling the formation of stars, planets, and human bodies. As the universe continued to expand and cool, it reached the Hadron epoch at approximately 1 microsecond. During this phase, the temperature dropped enough for quarks and gluons to condense and form the first stable composite particles, protons and neutrons. By the end of this pivotal first second, the basic laws and constants that govern physics and chemistry, the parameters that dictate the orbit of planets and the firing of neurons, were finalized and set in stone. In this single, fleeting second, the entire framework for the cosmos was established. Every structure, every chemical reaction, and every law of motion owes its properties to the conditions set during that initial, rapid burst of change. The most profound piece of physical evidence confirming this beginning is the cosmic microwave background, radiation. The CMB is the residual heat and light left over from the early universe, specifically from a time approximately 380,000 years after the Big Bang, when the universe finally cooled enough for the first neutral atoms to form. Before this moment, the universe was an opaque plasma. Once atoms formed, light was released, and that ancient light, stretched and cooled by billions of years of cosmic expansion, now fills all of space as a uniform background glow at a temperature of about 2.7 degrees Kelvin, which is approximately minus 270.45 degrees Celsius. The tiny, fractional temperature fluctuations within the CMB are the direct imprints of the density differences established during the inflationary epoch, providing an astonishingly accurate link to the very origin of time. If time had a violent beginning, cosmological models dictate that its eventual destiny is a state of near-perfect stillness, known as heat death. The universe continues its accelerated expansion, driven by dark energy. As this expansion proceeds, the energy and heat within the universe spread thinner and thinner. This inevitable process leads to a state of thermodynamic equilibrium, where all energy is distributed uniformly, and the temperature approaches absolute zero. Once equilibrium is reached, there is no energy gradient left to drive any physical process, and meaningful change ceases. This far future scenario is defined by immense cosmological eras, beginning with the degenerate era. After 10 to the power of 14 years, all current stars will have died, and the fuel necessary for new star formation will be completely exhausted. The universe will then be populated only by cold stellar remnants, including white dwarfs, brown dwarfs, and neutron stars. The last source of significant energy during this phase will be generated by the occasional collision of these cold, dense objects. Crucially, during this era, matter itself is hypothesized to become unstable. Though the process remains unconfirmed, current theories suggest that protons will eventually decay, a phenomenon known as proton decay, with a half-life possibly greater than 10 to the power of 37 years. This decay will convert the last remnants of organized atomic matter into radiation, such as positrons and photons, effectively eliminating the final vestiges of normal atomic structure. Following this, the universe enters the black hole era, spanning from approximately 10 to the power of 40 years to 10 to the power of 100 years. During this unimaginably long period, the primary massive objects remaining will be black holes. Stephen Hawking theorized that these objects slowly lose mass over time through the emission of Hawking radiation, causing them to eventually evaporate. A typical solar mass black hole takes approximately 10 to the power of 67 years to fully dissipate. The largest supermassive black holes will take even longer, perhaps up to 10 to the power of 100 years to finally dissipate completely. The final cosmological epoch is the Dark Era, which begins beyond 10 to the power of 100 years. The universe becomes a vast, empty expanse dominated by a sea of extremely low-energy photons, neutrinos, and the highly dispersed remnants of electrons and positrons. By this time, there are no thermal gradients, no sources of organized energy, and no complex structures remaining. The universe reaches its state of thermodynamic equilibrium, marking the eventual cessation of physical change. While the heat-death model is the most widely accepted outcome based on current observations of dark energy, two other major alternatives are sometimes considered. The Big Crunch: if dark energy weakens or gravity proves dominant, the expansion could reverse. The universe would begin to contract, leading to a final collapse back into a singularity, potentially resetting time. The Big Rip: if the repulsive force of dark energy continues to accelerate, it could eventually become so strong that it overcomes all fundamental forces, tearing apart galaxies, solar systems, atoms, and finally, even space-time itself, in a singular, rapid event. However, in the prevailing heat-death scenario, when the universe reaches thermodynamic equilibrium, where all matter is cold, dispersed, and all energy is uniform, time, as a measurable physical variable, loses its meaning. The universe becomes a vast, quiet field of equilibrium, and the cosmic clock effectively stops ticking because there is no remaining process left to measure. The journey from the Big Bang to heat death frames the entirety of time. Within that immense scale, humanity developed methods to capture and measure the flow of time for daily life, transitioning from merely sensing cosmic rhythm to engineering precise measurement systems. Early human dependence on the cycles of light and darkness spurred the invention of mechanical timekeeping, moving beyond the simple gnomon shadow stick. These early inventions all sought to capture a naturally consistent motion, Water clocks. One of the earliest reliable devices was the water clock, invented in ancient Egypt and later refined by the Greeks and Romans. These mechanisms measured time by the slow, predictable flow of water from one container to another through a small aperture. The challenge of the clepsydra was maintaining a consistent flow rate as the water pressure decreased as the source vessel emptied. Later designs incorporated complex floats and siphons to normalize the pressure, turning this simple flow into a stable, measurable heartbeat of the day. Hourglasses. The hourglass provided a significant technological leap. It relied on the measured, consistent flow of fine, dry sand through a narrow neck. Because the flow rate of granular matter is less sensitive to temperature changes and pressure variations than water, the hourglass offered a much more linear and reliable measurement for specific, fixed intervals, such as a sermon, a cooking time, or a watch at sea. These early clocks were the necessary predecessors to the great age of mechanical timekeeping, which began with the invention of the pendulum clock by Christian Huygens in the 17th century. Huygens used the predictable, gravity-driven oscillation of a pendulum to create a clock whose accuracy was dictated by the unyielding consistency of Earth's gravity. This reliance on a physical law for consistent motion culminated in the invention of the atomic clock, which uses the internal, reliable frequency of light, bringing us full circle back to the absolute constant that defines time itself. The invention of mechanical clocks, utilizing gears, springs, and pendulums, made time audible and synchronized society. However, these devices were fundamentally limited by environmental factors, gravity, friction, and thermal expansion, meaning their accuracy could never be absolute. This necessity drove scientists to seek a time standard rooted not in mechanics, but in the unchanging laws of nature. The solution was found within the atom. This realization led to the development of the atomic clock, the most stable timekeeping device known. The core principle leverages the quantum behavior of electrons. Inside an atom, electrons occupy discrete energy levels. When an electron jumps between these precise levels, it emits a burst of electromagnetic energy, specifically microwave radiation. For the standard atomic clock, the element cesium-133 is utilized. The official second is defined by the exact number of cycles of microwave radiation emitted during the specific transition, known as the hyperfine transition. This value is fixed at 9,192,631,770 cycles. This astonishing consistency, unaffected by temperature, air pressure, or magnetic fields, when properly shielded, allows atomic clocks to maintain accuracy that would deviate by less than 1 second over hundreds of millions of years. Atomic clocks now define international atomic time, serving as the temporal foundation for global coordination. Every mobile phone signal, every GPS satellite orbit, and every synchronized data packet across the internet is governed by the silent, billion-cycle beat of the cesium atom. This reliance on quantum mechanics allows global civilization to operate with temporal harmony, from coordinated mass transit systems to high-frequency financial trading. Despite this external precision, the individual human experience of time remains intensely subjective. The psychological second often diverges dramatically from the physical second. This divergence emphasizes that, while physical clocks measure duration, the human brain measures meaning and change. A second spent in a high-alert situation such as a near-miss traffic incident, feels subjectively much longer than a routine second spent waiting. This is because the brain's internal processing speed, influenced by neurochemistry, is highly variable. The physical clock provides the timeline for external events, but the internal experience of aging, memory, and rhythm is measured by the mind's engagement. Clocks are necessary for global coordination. Individual perception determines the value of existence. In the vacuum of deep space, the challenges of timekeeping escalate. The natural environmental cues that shape time on Earth, the rotation, day, night, and stable gravity, are absent. While the laws of physics persist, the practical anchors for both navigation and biology are removed. Deep space exploration necessitates extreme temporal precision because of the immense time delay inherent in radio communication. When engineers send a command to a distant probe, such as Voyager 1 into the outer solar system, the radio signal, although traveling at the speed of light, takes many hours to reach its destination. Consequently, engineers must precisely pre-calculate and program commands to be executed hours after transmission. For example, a command to fire a thruster might be programmed to activate exactly 4 hours and 15 minutes after receipt, meticulously compensating for the round-trip light time to ensure the maneuver occurs at the correct moment in space. This reliance on predicting the future state of a system based on hours-old information confirms the non-absolute nature of time across vast distances. The clocks carried by the probes, miniaturized atomic timekeepers, must constantly be corrected for relativistic effects, time dilation due to velocity and gravity gradient, to ensure their onboard timing aligns perfectly with Earth's reference time. The absence of a stable 24-hour light-dark cycle profoundly affects the human body's internal timekeeper, the circadian rhythm. This biological clock, governed by the suprachiasmatic nucleus, SCN, is designed to reset daily based on the presence of bright light. In space, this synchronization is lost. Astronauts often experience circadian drift, where their natural sleep-wake cycle deviates slightly from the rigid operational schedule. Without the intense blue light frequency provided by the rising sun, the SCN struggles to regulate hormones like melatonin and cortisol. To mitigate this, crews must follow strict artificial light protocols using specialized blue-rich lighting at precise times to simulate the effect of Earth's sunrise, actively enforcing a consistent operational day onto the body's drifting biological clock. This demonstrates that in space, time is a dynamic resource that must be technologically enforced on both biological and mechanical systems. Having explored time from the quantum level to deep space communication, we confront the enduring question: what is time? Physically, time is fundamentally the fourth dimension of space-time. It is not an external flow, but an intrinsic coordinate that allows physicists to place every event precisely within the universe's geometry. Time is the axis along which change must occur. In the context of relativity, time is defined as the measure of the separation between two events in a single reference frame. This geometric definition clarifies why time can stretch or compress. It is a flexible coordinate that adapts to motion and mass to maintain the constant speed of light. A major unresolved issue in physics is the arrow of time, the observation that time only moves forward, distinguishing the past from the future. Most fundamental physical laws, such as those governing gravity or electromagnetism, are time-symmetric. They work equally well, forward or backward in time. The most widely accepted explanation for the arrow of time lies in thermodynamics, specifically the second law of thermodynamics, which states that the entropy of a closed system must always increase, because the universe began in a state of extremely low entropy, high order at the Big Bang, and is irreversibly moving toward a state of maximum entropy, heat, death, this one way. Irreversible increase in disorder provides the only fundamental physical directionality for time. Every event, from the cooling of a cup of coffee to the decay of a star, increases entropy and defines the forward march of time. At the scale of quantum mechanics, the conventional concept of time becomes increasingly ambiguous. In many key quantum equations, such as the Wheeler-DeWitt equation, which attempts to unify quantum mechanics and general relativity, the variable for time appears to disappear altogether. This mathematical result has led some theoretical physicists to propose that time may not be a fundamental entity of the universe. Instead, time may be an emergent property, a statistical construct that arises only when vast collections of matter, like stars or brains, interact and move irreversibly from a state of order to disorder. Under this view, the universe at its deepest level simply is a state of timeless being, and time is merely the essential psychological and thermodynamic tool we use to observe, measure, and assemble the narrative of change. Scientists calculate the universe's age to be approximately 13.8 billion years by relying on precise observations of the cosmos, primarily confirmed through two independent methodologies. The first method uses the cosmic microwave background, CMB. The CMB represents the oldest light we can detect, emitted about 380,000 years after the Big Bang, when the universe cooled sufficiently for atoms to form. By precisely measuring the temperature and tiny fluctuations within this relic radiation, cosmologists can accurately calculate the rate at which the early universe cooled and expanded from its initial hot state. The second methodology centers on the Hubble constant and galaxy recession. This technique relies on measuring the rate at which galaxies are moving away from each other, their recession velocity, which is a direct indicator of the universe's ongoing expansion. By measuring the distance to countless galaxies and calculating the rate of expansion known as the Hubble constant, currently around 70 kilometers per second per megaparsec, scientists can mathematically extrapolate backward to the singular point when the expansion began, confirming the overall age of the cosmos. Further confirmation comes from Big Bang nucleosynthesis, BBN. This theory successfully predicts the cosmic abundance of the lightest elements, hydrogen, helium, and trace amounts of lithium. The BBN process occurred within the first few minutes of the universe, and the predicted ratios of these elements align almost perfectly with current observations. Since the ratio of helium to hydrogen is highly sensitive to the total density and temperature of the universe in those first critical minutes, this concordance acts as a powerful verification of the conditions used to calculate the universe's overall age. These measurements place humanity firmly within the grand cosmic narrative. The universe began in the chaotic first second. The period immediately following, lasting until roughly 0.5 billion years later, saw the end of the cosmic dark ages and the birth of the first massive, short-lived stars. Their explosive deaths seeded the universe with the heavy elements necessary for complex chemistry. Approximately 9 billion years after the Big Bang, our own solar system formed. Our sun began its life, and the Earth aggregated from the enriched gas clouds, we live at the 13.8 billion year mark, the present day. Humanity exists as the conscious product of this vast history, observing and measuring the universe that created us during its active, middle-aged phase. We are inherently aware that time moves in only one direction. We remember the past, but we cannot access the future, and we never observe events unfolding in reverse. This fundamental asymmetry, known as the arrow of time, is one of the deepest mysteries in physics, especially since most fundamental laws governing particle interactions are time-symmetric. If you filmed the collision of two subatomic particles and played the film backward, the physics would still hold true. To understand why time has a direction, we must turn to thermodynamics, specifically the second law of thermodynamics. This law states that the entropy of a closed system must always increase. Entropy is precisely defined as a measure of the number of possible microscopic arrangements, microstates, a system can have. A low entropy state is one of high order and limited arrangement possibilities. For example, a deck of cards, perfectly sorted. A high entropy state is one of high disorder and numerous arrangement possibilities. For example, the same deck of cards shuffled randomly. The flow of time is dictated by the universe's inexorable movement towards states of higher entropy. Consider a simple example. If a drop of red ink is placed in a glass of clear water, the ink molecules initially occupy a limited, ordered space, low entropy. Given time, the molecules will naturally disperse to uniformly color the entire volume. High entropy, the statistical likelihood of the ink spontaneously regathering into a drop, reversing the process, is virtually zero. Time flows forward because there are vastly more ways for systems to be disordered than ordered. This statistical preference for increased entropy is what draws the arrow of time from the past to the future. The universe began in a state of remarkably low entropy, the highly ordered, dense state after the Big Bang, and time is simply the continuous measurement of this universal tendency toward increasing disorder. Every event in our lives, from the burning of fuel to the formation of a memory, increases the total entropy of the universe, irreversibly defining the direction of the past and the future. While the arrow of time dictates the direction, general relativity dictates the shape and flexibility of time itself. Time is not a fixed background. It is the flexible fourth dimension of space-time. This geometric view leads to the concept that the flow of time is local and intensely responsive to physical conditions. We know that time flow is affected by two primary factors, both of which demonstrate that time is not universal but local. Firstly, increased speed causes time dilation, governed by special relativity. As the velocity of an object increases, its available motion budget shifts toward the spatial axes, forcing a slower progression along the time axis. Secondly, increased mass and gravitational field strength cause gravitational time dilation, governed by general relativity. Time slows down where space-time is most curved. These measurable effects confirm that the universe is not ticking in unison. Every individual clock, whether mechanical or biological, operates at a slightly different tempo depending on its world line, its specific path through the curved spacetime. The internal logic of relativity ensures that for an observer's personal reality to be consistent, time itself must adapt to their unique motion and location. Some theoretical physicists have explored mathematical models that challenge the linearity of time, such as conditions that could create closed time-like curves, CTCs. A CTC is a hypothetical path through spacetime that loops back to an earlier point in time, essentially creating a time machine. These concepts arise in extreme theoretical geometries, such as near infinitely long rotating cylinders or specific configurations of wormholes. While CTCs are mathematically possible under certain exotic conditions, often requiring negative mass or energy, there is no observational evidence to suggest they exist. Many physicists believe that fundamental principles, such as chronology protection, which prevents the universe from allowing paradoxes, inherently prohibit CTCs, maintaining the strict, forward nature of time. For practical reality, the movement of time remains strictly unidirectional. The most dramatic physical evidence for the malleability of time occurs at the event horizon of a black hole, where gravitational curvature is maximal. The immense density of the black hole causes an extreme acceleration of gravitational time dilation. If an observer were positioned safely far away, watching a chronometer fall toward the event horizon, they would observe the warping of space-time through two simultaneous phenomena. First, they would see time itself stretch, observing the chronometer's clock slow down drastically, with seconds on the falling object's clock appearing to stretch into minutes and then hours. Simultaneously, the photons struggling to escape the black hole's powerful gravity would lose energy, causing a pronounced gravitational redshift. This redshift stretches the light into longer wavelengths, such as infrared or radio, making the object appear progressively dimmer and redder until it becomes completely invisible. From the external observer's perspective, the chronometer would appear to freeze just shy of crossing the event horizon, its time flow slowed to a virtual stop. The black hole is the physical location where the forward flow of time is most intensely warped, serving as a boundary between the time-bound universe and the unknown physics of the singularity. It demonstrates that time is not an external ruler for the universe, but an internal variable that responds to the sheer presence of mass. The ultimate consequence of the arrow of time is the impossibility of observing its reversal in any macroscopic system. Although the theoretical possibility of decreasing entropy exists, the statistical improbability of observing it is staggering. This statistical barrier exists because the number of possible disordered states, high entropy, overwhelmingly exceeds the number of ordered states, low entropy. Observing a broken window spontaneously reassemble itself, for instance, would require every molecule, dust particle, and acoustic wave involved to simultaneously and perfectly reverse its motion, an outcome so incredibly unlikely that it is considered physically impossible across the lifespan of the universe. This unidirectional flow is also locked in by our universe's cosmic direction. The cosmos began in a state of remarkably low entropy, highly ordered at the Big Bang, and has been committed to the high entropy path ever since. Reversing time would therefore require reversing the entire thermodynamic history of every particle in the universe, effectively unwinding the fundamental expansion and increasing disorder that has defined our reality since its beginning. Even if the arrow of time could be reversed by an external cosmic force, the subjective experience of an observer within that universe would remain unchanged. If all physical processes, including the formation of memory and consciousness, were reversed, the observer's subjective memory would also reverse. They would experience the reversal as a continuous flow forward, with thoughts, memories, and observations unfolding in a consistent sequence. The arrow of time is thus not only a statistical and cosmic truth, but also a psychological necessity for coherent consciousness. The past is fixed by entropy, and the present is defined by the irreversible accumulation of information. The human experience of time is profoundly altered during sleep, particularly during the phase known as REM, rapid eye movement sleep. Sleep is not a uniform state. The brain cycles through distinct stages of non-REM, NREM, and NREM sleep, with each full cycle lasting approximately 90 minutes. NREM sleep is divided into stages: N1, light, drowsiness; N2, where sleep spindles stabilize the mind; and N3, deep, slow-wave sleep, crucial for physical restoration. During N3, the brain's activity is highly synchronized and quiet. In contrast, during REM sleep, the brain becomes intensely active. Neurological scans show brain activity patterns closely resembling those of an awake, alert state, driven by high levels of the neurotransmitter acetylcholine. However, the body is simultaneously placed in a state of atonia or temporary muscle paralysis. This mechanism is actively triggered by the brainstem, specifically the pons, which uses inhibitory neurotransmitters such as glycine and GABA to suppress motor neurons, preventing the dreamer from physically acting out the vivid scenarios. This is where the temporal distortion occurs. In the waking state, our perception of time is anchored by external temporal cues, known as Zeitgebers. The most powerful of these is the cycle of sunlight, which resets the suprachiasmatic nucleus, SCN, the body's master biological clock. During REM sleep, the brain is effectively offline from external anchors, and the neurochemical environment is radically different. While acetylcholine, linked to memory and arousal, is high, the brain actively suppresses key waking neurotransmitters like norepinephrine, linked to attention, focus, and logical, linear thought, and serotonin, linked to mood regulation and impulse control. The suppression of these chemicals is why dreams are often illogical, non-linear, and emotionally volatile. The brain is not operating on the causal, linear logic of waking life. Event A leads to event B. Instead, it operates on associative logic. The dreaming brain functions like an editor splicing scenes together based on emotional relevance or fragmented memory recall, not chronological order. A visual of a high school hallway might instantly connect to a feeling of anxiety, which then connects to a new, unrelated visual that also produces anxiety. This associative, non-linear processing completely shatters the normal experience of time. A dream might compress the feeling of a long, complex journey into just a few seconds of REM, or it might stretch a single, fleeting thought into a seemingly endless scenario. Scientific studies confirm this mismatch. When participants are awakened during REM sleep and asked to estimate the duration of their dream, their guesses are often wildly inaccurate. The brain, when dreaming, is not simulating time, it is creating a narrative experience, and that experience includes its own flexible, distorted, and often looped timeline. If time is elastic in dreams, what is its ultimate fate in the physical universe? The concept of time ending is intrinsically linked to the concept of change. If time is the measure of change, then time effectively stops when all physical processes cease. Current cosmological observations, which show the universe's expansion is accelerating due to dark energy, point toward a scenario known as the heat death, or Big Freeze. This is not a sudden, fiery end, but a slow, gradual cooling and settling into a state of maximum entropy over trillions of years. This scenario unfolds in distinct cosmological eras: the stelliferous era, current era. The universe is rich with stars and gas, actively forming new stars. This is the period of maximum activity and complexity in the cosmos, and the degenerate era begins. After 10 to the power of 14 years, all star formation ceases as the available gas is exhausted. The universe becomes populated only by the remnants of dead stars, white dwarfs, neutron stars, and brown dwarfs. The only remaining energy is generated by the occasional collision of these cold, dense objects. During this era, matter itself is hypothesized to become unstable. Grand unified theories predict that protons will eventually decay, known as proton decay, while the half-life is immense, possibly exceeding 10 to the power of 37 years. Its eventual occurrence means that all normal matter, baryonic matter, will dissolve into a sea of leptons, like electrons, and photons, leaving no complex structures. The black hole era begins after 10 to the power of 40 years. In this era, the primary massive objects left will be black holes. However, these objects are not permanent. Stephen Hawking theorized that black holes slowly evaporate over time by emitting Hawking radiation. This quantum process occurs at the event horizon, where quantum fluctuations constantly create pairs of virtual particles, a particle and an antiparticle. Occasionally, one particle falls into the black hole, while the other escapes, carrying away a tiny fraction of the black hole's mass energy. This process is incredibly slow. A black hole with the mass of our Sun takes approximately 10 to the power of 67 years to fully dissipate. The largest supermassive black holes will last for up to 10 to the power of 100 years. The dark era begins after 10 to the power of 100 years. The universe reaches its final state. It becomes a vast, cold, empty expanse dominated by a sea of low-energy photons and neutrinos. No temperature differences remain, no complex structures exist, and no energy gradients are left to drive any physical process. In this state of thermodynamic equilibrium, all change stops. Because time is physically defined by the occurrence of events, the cessation of all events means the cosmic clock effectively stops ticking. Time, as a meaningful physical variable, ceases to exist. If time has a potential end, we must confront the most complex question: what came before time began? This question is a logical paradox, as the term "before" is a temporal word that requires time to exist. The Big Bang, which occurred approximately 13.8 billion years ago, was not an explosion in an existing space. It was the emergence of space-time itself. Therefore, according to classical general relativity, there was no before the Big Bang. This theory predicts a singularity at t equals 0, a point of infinite density and curvature. At this point, the mathematics of relativity, which involve dividing by 0 at the singularity, break down completely. Classical physics cannot describe this state, so it cannot answer what came before it, as the laws themselves cease to function. This is why quantum gravity theories are necessary. These theories attempt to describe the extreme conditions of the Planck epoch, the first 10 to the power of minus 43 seconds, where both quantum effects and gravity were significant. Some of these theories suggest time is not fundamental at all. Instead, it is an emergent property that arises from a more basic, timeless quantum reality, much as temperature is an emergent property of vibrating atoms, but a single atom is not hot or cold. The Hartle-Hawking state offers another perspective. This no-boundary proposal, developed by James Hartle and Stephen Hawking, uses a mathematical concept called imaginary time to treat time as a fourth spatial dimension at the very beginning. It suggests that if we could trace time backward, it would behave like a spatial dimension near the beginning. The universe would have a finite past, but no singular starting point or boundary. As Hawking famously analogized, asking what came before the Big Bang becomes as meaningless as asking what is north of the North Pole. The before simply doesn't exist in that geometry. Finally, string theory and brane cosmology propose cyclical models. Models such as the ekpyrotic universe, a form of brane cosmology, suggest that our three-dimensional universe, a brane, exists in a higher dimensional space. In this view, the Big Bang was the result of two branes colliding, which reset the cosmic clock and initiated the expansion. This model suggests a cyclical universe, implying there was a before, but in a form we cannot directly observe. While we cannot yet observe before the Big Bang, these theories challenge our intuitive assumption that time is a constant, linear flow, suggesting instead that it is a complex, emergent, and perhaps cyclical feature of the cosmos.